Hello. In this discussion, we'll be evaluating logarithms whose base is neither 10 nor e. Okay, so let's begin. So we're going to approximate a logarithm whose base is neither 10 or e. So you're like, well, what's so special about 10 or e? Well, 10 or e is numbers you can actually use your calculator. Because on calculators, scientific calculators, log base 10, common log, and log base e, natural log, those are actually two buttons on the calculator. So if you needed to calculate a logarithm with one of those bases, then you can use your calculator. We're going to still be needing our calculator for this one as well, but we don't have, in this example here, for example, a log. We don't have a base 3 on this one, so on our calculator. So log base 3 of 12. So we need to figure out a way to do this with using the calculator, but without having to have a log base 3 on a calculator button. So a round answer to the 4 decimal places. So we're going to do is we're going to set that equal to y. Now again, we did a problem like this in a similar video. What we need to do is figure out what y is. So we need to change this to exponential form. So the first thing we do is change this to exponential form. So it'll be 3 to the y power equals 12. And there it is. Okay. Now, you know 3 squared is 9. So you know 2 is too small. Now, 3 to the third is 27, and 27 is a lot bigger than 12. So 2 is too small, 3 is too big, but we know it's somewhere between 2 and 3. That's good to know. Okay? But how are we going to get y by itself? Well, in the previous video, we learned that if we have two numbers that are said to be equal, then you could take the log of both sides. Okay? So you can take the natural log of 3 to the y equals the natural log of 12. Guys, you can very easily use a common log as well. Common logs are okay as well. I like the natural log better because it's got one less letter in the abbreviation ln as opposed to log, which is not a big deal. But a lot of times you will be dealing with the e function, e to the x power. And so ln would be a very, very good one to use there because things would get dropped off rather quickly. So it's a good form just to use ln and not log, even though you'd get the same answer in this case if you try to use the common log button. Okay? So we've got natural log of 3 to the y equals the natural log of 12. Now remember, we're trying to solve for y. So what we're going to do now is what? Well, how are you going to solve for y when it's written up there? You're not going to get it if it's written as an exponent. So it needs to go in factored form. Are you allowed to bring that y out front? Yes, because of the power law. So y times the natural log of 3 equals the natural log of 12. And if your goal is to figure out what y is, wouldn't it be imperative to get rid of that natural log of 3? Well, what's the operation between them? It's a multiplication. So we need to divide by the natural log of 3 to the other side. Now, so y equals the natural log of 12 divided by the natural log of 3. Now, many good students will fall in the trap right here. Okay? So what they'll do is they'll cancel those ln's off. They'll think of it as a multiplication or something. So they'll end up with 12 divided by 3, which is 4. And they'll think, well, the answer is 4. Now, we've already established that the answer has got to be between 2 and 3 because 3 squared is 9 and 3 cubed is 27. One's too small, one's too big. So we know 4 couldn't be the answer. But that hasn't stopped a few students from just taking off those ln's. It's not legal to do that. These are functions. These are the natural log of 12. You're not allowed to cancel these off. You're not multiplying the ln times 12. You're taking the natural log of 12. You're taking the natural log of 3. And so you can't just just cancel those ln's off. But this was a good example because here, if you try to do that, you fall in that trap, you would think, well, it's 12 divided by 3, which is 4. We already established that's between 2 and 3. So you're like, what do you do now then? Well, you either stop here, and that's the exact value, or you can now pull out your calculator because now the calculator has an ln button. So now you know why we'll use ln or log because those buttons are on the calculator. So when you got 3 to the y equals 12 on that second step, you could have taken the log base 7 of both sides. Wouldn't help you any because you don't have log base 7 on there. So we choose either ln, which is what we did here, or the log button. You pick. But again, I would use the ln just as a rule of thumb. So you take the natural log of 12 divided by the natural log of 3, and you get 2.2619. That's an approximate value. Now remember, now let's kind of go back to what we began. Remember, it said 3 to the second is too small, 3 to the third is 27, is too big, and the answer is 2.2619. Now, what I do sometimes is put that back in there. Take 3 and raise it to the 2.2619. You won't get exactly 12. And you're like, why not? You're supposed to get 12. Well, this is only an approximate value. So if you approximate it down to 2.2619 and you take that number and raise 3 to that power, you're not going to get exactly 12 because you rounded it off. So, but I will tell you, you'll get really close to 12. You'll either get 11.999 or you'll get 12.001 or something like that. But you'll get something very, very close to that. So if you go out to more than 4 decimal places like you did here, 2.2619, maybe you go out to 5 or 6 decimal places, the more you go out, the closer you'll get to that 12. So now, do I need to do that? It's good for tests if you have time. If you're taking a test, and just to help you from not making a silly mistake. But 2.261, try that number in there and see if you get a number that is very, very close to 12. And if you do, you're pretty confident. And confidence is key on tests. You've got to be confident. All right, so let's look at the change of base theorem. Now, the change of base theorem will allow you to do these ones that we just did without doing all the equation solving, because it doesn't all work for you. It's called the change of base theorem. So if A and B are both not equal to 1 and m is a positive real number, then the log base A of m is the log base B of m divided by the log base B of A. Now notice, so you can take, if you're taking the log base A and the base is A, you could change the base to some other number like base B. But then you write it as a quotient of 2 logs. So log base B of m, the original input, divided by the log base B of A, and A is the original base. So this can be proven. It takes about 4 steps. Again, it's beyond the scope of what we need to do in this course. I believe it's in the book. If you request it, I can send it to you. If you want to see why the change of the base formula actually works, request that, and I'll send it to you personally. Some people like that. Some people like to see why things are the way they are. And I appreciate those people who do ask that. All right, so you take the log base A of m, all right, equals the log of m divided by the log of A. You're like, well, what's the difference here? Notice there is no base down there. It's a common log. So these two are just specific examples. So you remember base B on the original formula, as long as it's not equal to 1, you can use it. But what they're doing on these bottom two is they're changing it to a specific base. Why would you think they would do that? Because if you change base A to base 7, for example, if you have log base A of m equals the log base 7 of m, you can't do that one either because you don't know what base 7 is on a calculator. So the reason they're choosing these two right here on the bottom is because they know you can use your calculator. So the last two that you're seeing on this screen is this also the change of base theorem, but specifically they're using base B to base 10 on the first one and base B to be base E on the second one. And again, that second one is my favorite. Log base A of m is the natural log of m divided by the natural log of A. So, but you can use common logs of A. Now guys, don't misinterpret what this is saying. The log base A of m equals both of those. That doesn't imply that the log of m is equals to the natural log of m, nor does it imply that log of A is the same thing as the natural log of A. Because as we know, two fractions can be the same value without the numerators and the denominators being the same. For example, 2 over 4 is 0.5, and 1/2 is 0.5. But 2 doesn't equal 1, and 2 does not equal 4. So also, like for example, 2 over 4 equals 3 over 6. They're both 0.5, but 2 doesn't equal 3, and 4 does not equal 6. So the ratios are the same, but they don't have to be, the numerators don't have to be the same. So if you have log of m divided by the log of A, that does not tell you that the natural log of m is the same thing as the common log of m. So it's their ratios that have the same value. So if you divide these using a calculator, they'd be the same number. So let's look at an example. So we're going to approximate the log base 5 of 89. And we're going to evaluate log base square root of 2 over square root of 5. And we're going to round to 4 decimal places. So let's look at the first one. And look at how they did it. They did both of them. They did a common log and a natural log. So the log base 5 of 89 is the same thing as the log of 89 divided by the log of 5. And to tell you the truth, that first decimal, 1.9, yada yada, and all those decimals, I don't bother with that. I go directly to the answer. I just use my calculator, log of 89 divided by the log of 5, and it's 2.7889. Okay? Now, that's what the log of 89 divided by the log of 5 is. If you do it the other way, take the natural log of 89 over the natural log of 5. Now, notice the natural log of 89 was 4.48, whereas the common log of 89 was 1.9. So it's not the same number. But look at their answers. Their ratios are the same, 2.7889. But look at the numerators and look at the denominators. They're not the same values. So that's what I was discussing a while ago, that the numerators and denominators are not necessarily the same. So that tells me that the log of 5 is not the same thing as the natural log of 5. But when you divide them out with their ratios, they give you the same decimal equivalent. Alrighty, so let's look at the next one. Log base square root of 2 of the square root of 5. So it would be the log of square root of 5 over the log of the square root of 2. Then what they're doing here is they're taking those square roots and writing them as 1/2 power factors, and then they cancel. You're like, well, do you have to do that? No, you could actually just take the log of the square root of 5 on your calculator and let it do it for you. But then you take the log of 5 divided by the log of 2, and you'll get 2.3219. And if you do it using natural logs, same thing, to take the 1/2, cancel them out. It'll be the natural log of 5 divided by the natural log of 2. It's the same number, 2.3219. So the decimal equivalence, but the log of 5 does not mean it's the same thing as the natural log of 5. All right? All right. The next screen is a summary of all these videos for this section here. All right? So if you haven't wrote them down already, this would be a good time to pause the screen and write all these things down on an index card. And these are things that you just have to memorize for the exam. You just got to know them. That doesn't guarantee you're going to make an A if you know these, but it just tells me if you don't know these theorems and these properties here coming into the test, you're not going to know how to expand things out, what you need to. For example, to change the base theorem. If you don't know that theorem, and if I ask you to evaluate something that required to change the base theorem, then you're going to be hurting. So if you haven't done so already, you need to pause the screen, write these down on an index card or on a piece of paper at some point. Okay? And you need to know them. Okay? So if you have any questions on this video or anything else, you feel free to contact me, and you have a good day.